Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing about a very important class of organometallic compounds, namely the transition metal sigma alkyl complexes. Now, we have looked into kind of interaction that occurs in these type of complexes, and interaction wise there are two types usually prevalent for transition metal organometallic complexes, and these are ligand to metal sigma interaction or metal to ligand pi back donation. Now, what we have come across is that depending on this ligand or variation of this ligand, the extent of these interaction change. In this perspective, we have looked into several kinds of transition metal sigma alkyl complexes, right from the ones that we have I am talking about is Tm sigma R H or sigma alkyl complexes. We have also looked at Tm sigma R F, which are perfluoroalkyl complexes, and in the last lecture we have been talking about aryl complexes. And what we have seen that the extent of metal ligand sigma donation, ligand metal sigma donation or metal to ligand pi back donation, the interaction in all of these type organometallic complexes vary. Now, with that being in mind, we have also discussed that these transition metal sigma aryl complexes, they are intermediate between sigma alkyl ligands and pi acidic COPR3 ligands. Now, what does this mean? This means that in sigma alkyl ligands, the extent of metal to ligand back donation is minimal, whereas in pi acidic ligand the extent of back donation is significant. As a result, this aryl ligand has back donation which is more than that of the sigma alkyl complexes, but their back donation is much less than that of these pi acidic ligands. So, that is why these transition metal sigma aryl complexes lie in between sigma alkyl and pi acidic ligand complexes. I will illustrate this with example on their stability. So, transition metal in comparison to transition metal aryl and transition metal sigma alkyl complexes, transition metal sigma aryl, as they have more metal to ligand pi back donation than the sigma alkyl ones, these are slightly more stable than the transition metal alkyl complexes. To illustrate this, let us take a look at the two compounds. One is titanium tetraphenyl containing a titanium aryl bond and titanium tetramethyl. Now, titanium between these two, titanium tetraphenyl is more stable as this one decomposes, as the compound decomposes above 0 degree centigrade, whereas titanium tetramethyl is so unstable that it decomposes at minus 40 degree centigrade. In our earlier discussion, we have referred to the reason for this high instability of this titanium tetramethyl as it decomposes by molecular pathway. And also that it leads to decomposition owing to its electronic as well as steric unsaturation. Now, in titanium tetraphenyl, the electronic unsaturation is same as that in titanium tetramethyl, because both of these are 8 valence electron compounds. So, electronically they are equally unsaturated. However, as phenyl groups are more bulkier than the methyl groups, sterically titanium tetraphenyl is more saturated. Bigger phenyl group than the methyl ones. As a result, titanium tetraphenyl is more stable than the titanium tetramethyl. The second reason for extra stability apart from the steric can also be metal to ligand pi back donation, which is more in titanium tetraphenyl than in titanium tetramethyl. So, metal to ligand pi back donation is more in this, which leads to this extra stability of titanium tetraphenyl complex. As a result, between these extra sterics that the aryl brings and also because of the extra interaction of transition metal with the empty ligand orbital or metal to ligand pi back donation, the transition metal aryl complexes are more stable than transition metal alkyl complexes, and the transition metal aryl bonds are more stronger than the transition metal alkyl bonds. For example, the bond energy of metal transition metal phenyl is about 10% higher than the corresponding bond dissociation energy of transition metal methyl bonds. So, what we see is that because of transition metal to ligand back donation that occurs in transition metal aryl complexes, these can be more stable than transition metal sigma alkyl bonds. Let me illustrate this with few more examples in the subsequent slides. Also, another interesting observation unique to this transition metal sigma aryl complexes is sigma to pi conversion. And this is an interesting way in which a metal aryl sigma bond gets converted to a pi bond and was successfully used to prepare first bis-arene metal sandwich complexes. Would illustrate this with an example. For example, this is eta 1 C6 H5 whole 3 chromium THF whole 3 complex when heated or in ether in presence of H2O, oxygen and sodium salt gave a mixture of the sandwich chromium of C6H6 eta 6 type plus biphenyl C6H5 eta 6 C6H5 chromium C6H6 plus X minus plus bis biphenyl type plus X minus. So, This is an interesting example and unique to transition metal sigma-aryl complexes, that they can go or they can undergo a shift from sigma to pi bond. This was example where they are bound in a sigma fashion to the metal center, and then it binds with this pi cloud, and there are 3 C6H5 moieties bound to chromium in a eta 1 fashion. When heated under this condition, gives the sandwich complex, whereby there are 2 benzene C6H6 bound eta 6 using the pi cloud to chromium, or it was 1 C6H5 ligand and resulting in this biphenyl ligand, which is bound using the pi cloud using a eta 6 to chromium, and the other ring is a benzene C6H6 ring again bound to chromium with pi cloud, and last the third mixture is about 2 biphenyl rings bound to chromium using its pi cloud, and this method was successfully used for preparing the first bis-aryl metal sandwich complex of chromium as shown here. Now, going back on the discussion, a ligand to metal sigma donation and metal to ligand pi back donation, we would see that how this or interplay between these two interactions affect the stability of transition metal aryl complexes. So, how does ligand to metal sigma donation and metal to ligand pi back donation affect the stability of transition metal aryl complexes. And this can be explained by square planar complexes of transition metal aryl square planar complexes, which have been rendered kinetically stable because of the interplay between these two types of forward donation and backward donation. And the best examples of these are square planar nickel, palladium, platinum complexes of formula mesetyl M P are kinetically stabilized. Let us illustrate this with the molecular orbital diagram for this kind of complexes. So, for example, for bis mesetyl this is a square planar complex and here the metal center is in plus 2. So, this is D8 square planar system. Now, let us look at it how the interaction occurs. So, let us say this is the x y plane, and the metal is sitting over here. It has two pair 3 ligands which are trans to each other as given by and this bond is along the axis and it has two aryl groups of the mesytyl moiety along this bond. Now, this mesytyl moiety is in a plane perpendicular to the plane of the paper, and this is designated by the wedge bond shown over here. So, it has along z axis empty space where it can undergo some kind of attack, electrophilic or nucleophilic attack, but because of the kinetic stabilization such attack does not occur, and this can be seen with respect to the orbital interaction or that occur between the metal to ligand pi back donation, and that takes place between a ligand metal orbital of appropriate symmetry interacting with ligand orbital, and as a result of this transition metal to ligand pi back donation, these compounds are kinetically stabilized. And this interaction is very strong, and that occurs because the orthomethyl groups forces a conformation that facilitates platinum or metal dxy to aryl pi star back donation, and shields metal from axial attack. The axial attack can happen from the z axis, and what is seen over here, that kinetic stabilization between the transition metal to ligand pi back donation sort of inhibits this kind of axial attack, thereby stabilizing transition metal aryl kind of complexes. So, let me summarize. In this lecture, we have looked into the orbital interaction leading to extra stability of transition metal aryl complexes, and what we had observed is that the interplay between the ligand to metal sigma donation and metal to ligand pi back donation play a vital role in bringing about extra stability to these complexes, and with regard to the stability, the transition metal aryl complexes lie between that of transition metal sigma alkyl complexes and that of the other pi acidic ligands like carbon monoxide PR3, where the extent of transition metal to ligand pi back donation is at the maximum. So, these interaction particularly the transition metal to the ligand pi back donation also brings about extra stability to these transition metal aryl complexes. We have also looked into another interesting feature of these transition metal aryl complexes in the fact that they can undergo sigma pi conversion. As a result, it gives various kinds of transition metal sandwich complexes which are also of very interest. So, with that, let me conclude today's lecture, and I look forward to the next lecture, in which we will discuss some more applications of this transition aryl complexes, and also take up transition alkyne complexes, which is a subject by itself. So, till then, thank you for being with me in this lecture, and I look forward to being with you in the subsequent lecture. Goodbye.